So I'm Carlos de Breuck. I'm an astronomer at ESO. I work on ALMA development and previously also for 18 years on APEX, from the ESO side. So I've spent a lot of time at the high sites. So that's why I got involved into the AtLAST project, doing the site selection. And now in the new project, we've moved on from site selection to site characterization. And basically that's the next 50 minutes. I wanted to introduce you a little bit what is this all about and where AtLAST would be hosted. So here you see a bit of an overview. You can, of course, go and look yourself a little bit where AtLAST would be located. So you see the central part of the ALMA array is here in the bottom. If you see my cursor here, there's the blue ALMA part is where the central part of the ALMA array. ALMA, of course, in interferometer spreads over a large part of the area. So there's extensions out into the Pampa Laboro area where Aste and Nanten are located, but also to the northwest and also out of the view to the southeast. So in the northwest, there's also an area, a few ALMA pads on this side here. And there's also the APEX telescope here on the Cerro Castor mountain in the middle of the view. There's also CCAT Prime and the Tao Observatory, the Tokyo Astronomical Observatory. And to the east, on the left of your screen, you will see Simon's Observatory, and where other telescopes like CLASS, Polar Bear, and CMBS-4 would be located in the future. So we already have a number of neighbors, and one of the things we absolutely want to do is build up good relations with our future neighbors in this area. So that is really a key importance to be really on good terms and share infrastructure with all the neighboring observatories. So there's two pre-selected sites. I will now show in this talk a little bit how we got to these sites. It's the two yellow pins you see here. Is AtLAST Site 1 here on the site next to the ALMA road, and there's an ALMA Site 2 here on the site. So what is important to know is on the difference between these two sites. You have the Cerro Toco mountain, which is the big whitish area here in the screen, and that is actually an open air sulfur mine that has been abandoned many years ago, like more than half a century ago. But this area here shields the telescope, this side at least, from the prevailing northwestern to western winds. And also on the east, we would be blocked by the prevailing, not the prevailing, but the winds, eventual winds from the east would be blocked. While on site 2, there's this little mountain here called Cerro Chico that is blocking a little bit, but not as much as on site 2. So we'll come back to this later. So I mentioned that there is the ALMA is already one of the biggest telescopes, of course, up there. And what you see here in the blue is the outline of the Atacama Astronomical Park, which is an area that was dedicated for astronomical observatories. And in there's the big gap here, which is the ALMA concession. So that's where all the ALMA telescopes are located. So what is important is to see that the Site 1, which is marked with a little red box here, is inside the ALMA concession, while the Site 2 is outside of the ALMA concession, but still within this astronomical park, which is deliberately to put new observatories. Now, going a bit more into details, Site 1. So here you have a zoom in. So you have the ALMA road here on the bottom that basically goes towards the central part of the ALMA array. So you come from the left and you go to the right around the corner. You already have, it's very near the APEX telescope that you can see here marked on the right center of the image. And there's also Cerro Chico, which is a transmission system, a wireless transmission system for APEX to go down to the base camp in San Pedro. So it's actually that area is right in between. And how does it look like from the ground? Well, it's a very nice flat area, rocky. So there's a lot of space to put a big telescope, and we do need a lot of space. So that's, of course, you cannot put such a big telescope as AtLAST at any possible location. You need space for it. You need a few hundred meters area on side by side. So it's also very near the ALMA road. So here, if you look well, you can even see the ALMA transporter on the road. So the AtLAST Site 1 is actually on the left of this picture here, and you have actually the ALMA fiber and power cables are also underneath between the road and this potential site. Now, Site 2 is, of course, a bit further north. Of that, it's about 4 kilometers away from Site 1. You already have another road here, which is the road of the astronomical park that you see going from the bottom right, the bottom center to the left of the image. And you have this this valley that comes down. It's like basically a floodplain from the two mountains, so the Cerro Toco on the north and the Cerro Castantor on the east. So you have, well, it is a very dry site. So you have flooding once every century or so. But the flooding is basically is the white area. So the site is just outside of this, which is a few meters higher than it. So you will not get water there. It is a very, very dry site after all. So how does it look like from the ground? So you have two pictures. Again, you see a picture here on the left with a car on the road. So that's basically the picture taken from the central part of where you have the kink a little bit in the box. And then you have another picture here that is facing towards the east. And you already see one of our weather towers that I will introduce next with a car and a sort of power plant to it. So you see it's also a nice and flat area, lots of space, even more space in this area than on the site one. So how did we get to those two sites? So that's the work that has been done in the last 3 or 4 years already, or even more. So we wanted to go a site where you can do submillimeter astronomy. So you have to go high. So 5,000 meter is a bit of the minimum that you need. Some other observatories like CCAT Prime Feast are going even higher to 5,600. But this is getting really tough to work, and it's maybe good for a survey telescope, but for a big telescope with lots of instrumentation installations like AtLAST, I mean, this is not we want to stay a little bit below 5,500 meters because then that really is very difficult to work up there, and we don't have engineers and instrument installers working there. We want the site to be accessible, so that's why we were near the road. We want to use existing infrastructure, power cables, fiber optics, because we will have high data rates with AtLAST. We want stable atmospheric conditions, so we don't want to be somewhere just behind a mountain where we have lots of turbulence. We want not too much snow. Not too much lightning. We want especially low wind speeds and low spin speeds. At the height of a big telescope, it's different. It's quite different to build a 12-meter or a 50-meter telescope. So the structure is a lot higher. So we really need to know the vertical wind speed. And that's where I'll come next. We need to measure that. So we also want the area to be flat and large enough. And we don't want to be too close to our neighbors either, that we don't shield with a big telescope that is going 60, 65 meters high. You really would shield the field of view of, for example, an ALMA, and then on one of the extended pads, you don't want to be too close because that would not be very nice to your neighbors. So I was mentioning we need to measure the wind. So for this, we actually designed and installed these weather towers. So you see a picture and the design of it. So if you look well at the middle of that tower, you see an arm sticking out. That is actually an arm where we mounted an anemometer. And on the top, at 24 meters height, there is another arm. By having the two arms at different heights, we can extrapolate the measurements out to beyond the total height of these towers. So these towers have been deliberately built so that we can actually lower and raise them quite easily with just a four-wheel drive car like the one that is on the picture there. We can actually, with the cables, we can actually lower and raise it and do maintenance and reinstallations of the anemometers there and fix some small technical issues with them. We also have a lightning protection system because we don't want our anemometers to be hit by lightning, which unfortunately happened once. So that's why we did need to lower them. And we want these sites to be autonomously powered. So we have a solar power plant with batteries on it. So we are already sustainable even in our site selection activities. So how do the data from these anemometers look like? So on the top, you see the blue and black are the measurements at 12 and 24 meter. So you see a bit more scattering between them, but the main thing is the difference are very small, but it does give you the vertical gradient. And so that has already been demonstrated that we can do it. But of course, we want to make sure the time variation and the seasonal variations of this. So we need a bit more data to even extrapolate this. And on the bottom, you see the black and red plots. They basically show you the difference between the two sides. And so this is a 24-hour period. And if you see at night, you have lower winds. So the first half, the left half of the plot is basically the night, and the afternoon is the right part where you have higher wind. So you see that the red points stick out a bit more. The red points are site 1, while the black points are site 2. So this already gave us an indication from the early measurements that site 2 has significantly lower wind speeds, and it could be up to 15% more observing time on site 2 than on site 1, which is one of our main criteria for a telescope, a big telescope without a dome. You really have to make sure that it is at a site where you can operate it as long as possible. So now what remains to be done on these measurements, as I already mentioned, is like we want to have longer time to really get the seasonal trends of it. And for this, we have a system in here. So it's a picture of what is actually in this solar power plants. You see actually a screen and the batteries there and the solar inverters. So it all works relatively easy with just a Raspberry unit, but we want this to be remotely accessible, that we don't have to go there and download the data manually from these anemometers. So that's the work that we need to do. We need to make sure that the data which we will make public are actually clean. So you see the anemometer here, actually, it's a zoom in of the anemometer. It's a sonic anemometer that gives us 20 hertz data. So really every 50 milliseconds, we have a time sample. So this is a lot of data, but also they're operating at 5,000 meters, which you normally don't operate these special sonic anemometers because the air density is about half of what you have at sea level. So they're not always made for these kind of conditions. So we really need to look carefully into getting the reliable data. So the main thing we not want to do in the coming years is really getting seasonal trends of this. So what we have looked at a bit of data, but we really need to look at several years of data to get a reliable seasonal trends to see which sites are better. And also, these data that we will measure will be feedback to the telescope design and also to the operations point of view. So like when can we do maintenance activities? When is the higher wind in the afternoon? Also at higher elevations, because we have some experience from the existing observatories, but there is more to be done. So I already mentioned turbulence, and that's the one thing that we have not determined yet. So here is actually an image that's not from Castantor. This is actually from Gibraltar. This is the Rock of Gibraltar, which you can actually find on YouTube, the video itself. I will play it now next. What you will see is that on the top of the hill, there is actually something called orographic forcing, which wind will be coming here from the left. And I will start the video now. So we'll see that it's higher wind on the top and you get turbulence on the back. So I hope this is working. Yes, so here you see the wind is going here, and afterwards you have higher wind. So you don't want to put your telescope on the top of a mountain, which you would think, but also you don't want to put it straight after it, because you get all this turbulence happening from the wind, basically the upward forcing of the wind stops at the top, and then you get lots of turbulence behind it. So this is exactly what we want to measure if we're far enough away behind the mountain that we don't have this turbulence anymore. And for this, we will actually have a small interferometer with satellite dishes. So basically commercial dishes that you would use to like, for example, communication satellites. So it's just 1 meter satellite dishes. And we want to make a small interferometer, and we track geostationary satellites to see the distortion of that signal. Now, going to the next one. We also looked a bit at snow coverage. So you see, these were images taken on the same day after a snowstorm. On site 1, you notice that there was more snow than on site 2. But of course, this is something we really want to measure over several years, and we want to have basically site inspections of it. We can also use satellite images, which we've already done to pre-select these sites, but we really want to do this a bit more detailed. So again, we want to make sure that we don't have too much snow. And site selection means not only looking upwards, but also downwards. So we want to see what kind of soil we want to build. And one of the things we want to do is to have a proper lightning protection. Here, site 2, because it was near this valley where we had flooding, and that's actually very good for lightning protection. So you want low resistivity, that you put a copper mesh in the ground to discharge the lightning charge strikes, and that actually is a lot easier on site 1 than on site 2 than on site 1. And you also see a picture here of how the soil looks like. It gets quite rocky if you go a little bit deeper. So these are considerations. And while site 1, we already have this report here on the right from Apex, which is very near, so we can assume that the site, the underground soil composition is going to be the same on site 1 and on Apex, while for site 2, we do not have this information. So that's one of the things we want to do in the coming 2 or 3 years, is to really make a detailed site soil study of site 2 to get the stability of the soil that we want, where we would like to install the telescope. So putting this all together, so that's basically all these different criteria that I mentioned. So green means good, yellow means okay, with a few warnings. Red means bad, and there is no red, so that is good. So that means that both sites are legible, but you see there's more green on site 2, which is now our conclusion from the site selection activities was that both sites are legible, but site 2 is the preferred one. So that's the picture of the site here. And so just concluding, what remains to be done is actually looking at and making sure that we can publicly make all of these weather tower data, these anemometer data available, because these kind of measurements do not exist anywhere yet. We want to make this really proper diurnal and seasonal trends. So really look at 3-4 years of data to see that we didn't miss any, we didn't get any special El Nino or La Nina seasons. We want to cover a few of those seasons to really get special trends, to see if there is one year where we really have much worse conditions on one side or another, and also to give that back to the telescope design, that we can optimize the design to withstand the conditions, but also not over-design, needlessly complicated the telescope design, because it needs to be based on fixed measurements. So we want to do this anomalous refraction, so basically this turbulence measurements, to make sure that we have the submillimeter seeing, because that is a problem that you get on a 50-meter dish surface and not on a 12-meter dish. We want to also make sure about the snow and lightning coverage, to make sure that we didn't overlook anything. We still have 2 potential sites, although we have a preferred site already. And we want to make sure that we have all the material to start a proper proper starting the design of the foundations of the telescope, and really give a proper cost price of how we would install. So that was it.